Okay, let's get started. Let's talk a little bit about next week. Next Tuesday, I will not be here. I'll be at a workshop in Santa Fe. So you will be having a guest lecturer on Tuesday. Frank Veenstra is a visiting PhD student from the University of Copenhagen in Denmark. There is a relatively large lab over there, also working on evolutionary robotics. Frank is spending the semester here at UVM, so I've asked him to bring in some of his evolved robots. He has both simulated and physical robots, so you'll get to see an actual robot in person next Tuesday. Frank will walk you through a little bit of his research project that has to do with a problem or an open challenge in the field called crossing the reality gap. So if you've got your robot to move already in simulation, what do you think would happen if you built two physical cylinders and attached them together and tried to get your robot to move in the way it's moving at the moment in your simulation?
It will not work.
It will not work. Why not?
Because the forces in reality is kind of different from the forces in the simulation.
Absolutely. So the forces in reality are different than the forces in simulation, right? So it's very unlikely that your two cylinders are going to stay upright and move for a while before falling over to the side, right? So already you've probably noticed that there's this big issue about what you evolve in simulation. It's challenging to get it to transfer to reality. Big open challenge in the field. Different people have different ideas about how to solve this problem. Frank will be here next Tuesday to walk you through a little bit about that. Okay, let's see. So next Tuesday, you can start in on assignment 4. So I won't be here on Tuesday to talk about assignment 4. So we'll spend a couple minutes this morning just talking about assignment 4. If you're not there yet, that's perfectly fine. Let's see. Today's lecture, we're going to still continue working our way through lecture 5 on evolutionary algorithms. We will probably finish that today. We might just start in on lecture 6. We'll see how far we get today. The reading for today is from the Open Dynamics Engine user guide. So underneath PyroSim is making use of an off-the-shelf open source physics engine called ODE. So in lecture 6 today and in the reading, you're going to see a little bit about what's going on under the hood in PyroSim and ODE. Okay, let's see. So the undergraduates, you are working on assignment 3, and you're implementing sensors. Sensors, like joints, can sometimes be a little bit tricky because they're invisible, right? So you can't always see where you're placing a sensor. And in the case of the ray sensor, it's tricky to see which direction it's pointing in. You can see it if you get the direction right, but if you don't get the direction right, it's difficult to see where it's pointing. So we talked about this last time. You're implementing 4 different sensors, 2 touch sensors, a proprioceptive sensor, and a ray sensor. And the ray sensor is similar to a joint in that you need to give it both a position in 3-dimensional space, and you need to supply 3 additional arguments, R1, R2, and R3. R1, 2, and 3 in the joint specifies the orientation of the joint. Specifies the plane through which the objects will rotate. So R1, R2 specifies that joint normal. In the case of the ray sensor, as you would imagine, R1, R2, R3 indicate the direction that it's supposed to point in. So towards the end of assignment 3, you're asked to move the ray sensor from the tip of the red cylinder pointing outward and move it so that instead it is, let's see if I can find it. It's here somewhere. There we, no, not that one. There we go. Okay. So you're then going to move ray 3 so that it's now sitting on the underside of the red cylinder and pointing down. If you don't get it in the right place and pointing in the right direction, you don't see any black line, and it's hard to know whether you've got things in the right place and pointing in the right direction. So here's a little bit of a hack for you. When you're placing an invisible element into PyroSim like a joint or a ray sensor, don't place a joint or a sensor. Place a cylinder that has a length of 0, which will give you a sphere that you can see, and put the sphere where you want the ray sensor to be. If you place the sphere there, it's not attached to anything, it'll just fall, but at least you'll be able to see, if you start the simulation in pause mode, you'll be able to see that you got the X, Y, and Z correct, right? You'll know whether your ray is actually sitting on the underside of the cylinder. Perhaps by mistake you put it inside the cylinder, or you only put it halfway up towards the cylinder, or what have you, right? So you can debug the X, Y, and Z coordinate of, in this case, the ray sensor. How can you use the cylinder then to debug the direction in which the ray sensor should point? So you want to add the ray sensor, but you've commented out the ray sensor for the moment. You've put a sphere where the ray sensor should be, and you change the X, Y, and Z of that sphere until the sphere is sitting right on the underside of the red cylinder. So now you know what the X, Y, and Z coordinates should be for the ray sensor when you comment out the cylinder and put the ray sensor there. But how can you figure out direction? You want to make sure that the ray sensor is pointed in the right direction.
Could you make one end of the cylinder capped so that if the capped end would be showing?
That's it, right? So all of the cylinders in PyroSim by definition are capped, right? So if we've got our red cylinder here, and we place a cylinder with length 0 here, we can figure out the X, Y, and Z coordinate of where the ray sensor should be. We want, as our engineering drawing shows us, we want the ray sensor to point down. So if we change the length of this cylinder to something that's non-zero, now we have a cylinder that's centered at this position. And by setting R1 and R2 and R3 of this cylinder, we can see from the orientation of this cylinder that it's going to match up with the direction in which the ray sensor should point. So perhaps in the assignment we actually wanted the ray sensor to point down and forward. So you got to remember your coordinate frame to figure out what that is. Try and set the R1, R2, and R3 of this cylinder so that the cylinder points, quote unquote, in the direction that your ray sensor is going to point. So you can use a visible element, a cylinder, and set the X, Y, and Z and the R1 and R2 and R3 of that visible element to figure out what the X, Y, and Z and the R1 and R2 and R3 of the ray sensor should be. So once you've got that straight, then you can comment out your cylinder, so the cylinder is no longer there. Put the ray sensor back in, and you should now have the ray sensor sitting in the right position and pointing in the right direction. Make sense? Okay, as you've probably figured out, in a couple of assignments from now, you're going to be making a much more complex robot than this. So you're going to want to use these kind of hacks to figure out where the positions and orientations of all the objects and joints and sensors in your robot are going to go. Okay, let's see, other things to talk about. One of my graduate students, Anton, who has a Windows machine, worked with me. We figured out a fix for those of you that are having problems with your Windows machine on assignment 3 here. We figured out what the problem was. So I've now put the fix directly in at step 18 here, which is where many of you are starting to have problems. I've heard back from one of you that this solved your problem. So I think we found a good fix for anyone on a Windows machine. Yes?
I downloaded the new Thurs Feb PyroSim version, and I'm still getting errors.
Aha, okay. So not the final fix then, I guess. Okay. Come and see me after class and show me what error you're getting, and we'll go from there. Okay. We're going to actually talk again. We're going to sort of open up the hood today of PyroSim and see what's going on under the hood, and you'll be able to see a little bit more about what this fix actually is. Okay. So that's assignment 3. And again, next Tuesday I won't be here, but you will be starting in on assignment 4, when you will now be adding neurons and synapses to your robot. We've just finished talking about neurons and synapses, so you should be pretty familiar with them by now. So there are two Reddit projects inside assignment 4, the Neurons project and the Synapses project. Let's just have a very quick look at these so that you're oriented for next week. First thing you're going to be doing is adding some neurons. And remember from our discussion last time that in a neural network, we have an input layer, or our input neurons, and we have our output layer that's made up of output neurons. When we take a neural network and put it inside a robot, we don't talk about input and output, we talk about sensors and motors, right? So again, we're annotating our engineering drawing as we go. You'll notice we have added 2 sensor neurons, and these 2 sensor neurons are collecting the values from the 2 touch sensors. Now the sensor neurons are a little bit special because there is an arrow connecting this sensor to this neuron, which might suggest this is a synapse. In this case, the arrow is just showing that we take whatever the value is of the touch sensor, which, as you probably know by now, is either 0 or 1. We just copy that value and place it into the neuron. Yeah. Okay. So these 2 sensor neurons are collecting at every time step of the simulation the value of their respective touch sensor. And we then have a third neuron. So we have neurons 0, 1, and 2. We have a third neuron, which is a motor neuron, and it's attaching to the joint. Remember that in the way that we're going to set up these neurons, we're applying the tanh function to whatever incoming value is arriving at the neuron. So when we push a value through the tanh function, we get a number that comes out the far side, which is in the range of -1 to +1. So we know that when we run our simulation, whatever value is in the motor neuron here, it's going to lie between -1 and +1. You'll notice that we don't have any synapses yet. There are no connections between this going from the sensor neurons to the motor neurons. So when we start up this simulation, you now know what values are going to be arriving at the sensor neurons, 0 or 1, depending on whether its touch sensor is firing or not. What value do you think the motor neuron takes on? It has no arriving synapses. There's no external influence on this neuron.
The angle.
It's actually going to be sending, the motor neuron is going to be sending its value to the joint, and the joint is going to interpret that number as an angle, but what is that number to begin with? 0, right? There's no incoming influence, so the value here is just 0. We're taking that value 0, we're sending it to the joint, and the joint is interpreting that number as a desired angle. Remember that the joint rotates between +45 to 0 and up to -45 degrees. But the motor neuron is outputting a value between -1 and +1. So we take the value that's coming out of the motor neuron and we scale it so that it lies in the range -45 to +45. Okay, so this value of 0 is flowing to the joint, and it's commanding the joint to reach a desired angle of 0 degrees. What happens at the next time step? It stays 0, right? At the next time step, the motor neuron is still outputting a value of 0, so it's still telling the joint, hold a desired angle of 0. What do you think the robot does when you turn on this simulation, for those who haven't got this far yet? How is the robot going to behave? So when there wasn't a motor neuron attached to the joint was just free to rotate, right? The red cylinder would fall passively down towards the white cylinder and come into contact with the ground. So we have a ragdoll robot, right? It's just sort of flopping around. What's going to happen now?
Will it just like remain rigid when it falls?
Absolutely, right? So it's up in the air like this. The motor neuron is commanding the joint to hold the desired angle of 0. And we know that the starting angle of these two cylinders is 0. So it will just stay rigid, and it will just roll forward until the tip of the red cylinder comes into contact with the ground. That's about it. Your robot's not going to be doing anything fancy in this project. Okay, so that's neurons, right? So we've added some neurons, and they're doing their thing, but there's no synapses. There's no direct connection or no flow from any of the sensors to the motors, so the robot isn't going to do anything interesting. That's the neurons project. So then part 2 of assignment 4 is synapses, which we've seen a few times already. And again, we're going to continue annotating our engineering drawing. And now we're adding 1, and in some cases down here 2, synapses. So now the values of the sensor neurons are being passed on to the motor neurons. We can see that the weights of these 2 synapses, at least in this drawing, are both excitatory, right? Positive, +1. What does this robot do?
When a sensor is touching a surface, does it send a 1 to the motor so that motor would tighten?
Exactly, right? So already now we're back to Bratenberg vehicles. It's a little bit tricky now to figure out how this robot is going to move given this neural network. But I've tried to keep this robot simple enough that you can sort of figure it out, right? So here's our robot here. We can see at time step 0, the white cylinder is in contact with the ground, which means this touch sensor is firing. It has a value of 1. The red cylinder is off the ground, so its touch sensor has a value of 0. So at the first time step, the input layer, or the sensor layer, has a value of 1, 0. 1 times 1 plus 0 times 1 is 1. We pass that through the tanh function, which gives you about, I think, plus 0.7 or 0.8, whatever it is. It's something greater than 0. What does the robot do? How does the robot move at the next time step?
Well, after it touches it, it'll close up.
It'll flex, right? Remember that a desired angle of plus means that the motor neuron is commanding the joint to rotate inward to some positive desired angle. The motor neuron ranges between -1 and +1. We scale that to a value between -45 and +45. We've now figured out that our motor neuron has a value of plus 0.7, something like that. So it's commanding the joint to rotate to about plus 40 degrees at the next time step.
Depending on how fast it does that. If it goes slow enough, then it might stay at that angle until it falls. But if it goes fast enough, it could pick up its original leg and spread back out.
Absolutely, right? So it matters now how fast and strong the motor is. In later assignments, you're going to be able to tune the strength and the speed of the motors. We're not there yet. At the moment, the motor is relatively slow and weak. So it is going to flex in a little bit. You'll see it actually start to pull inward faster than it would if it was just falling passively. But it's not going to get to 40 degrees from one time step to the next, right? The motor's not that fast. It's going to move in a little bit. What happens at the next time step? So t equals 1 now, rather than t equals 0.
It checks motors, responds to the 1 out input.
Well, remember we're at the next time step, so we can't start with the motors yet. We got to start from
Next
sensors and
sensors,
flow all the way down. So what are the sensors doing at the next time step?
It should still be outputting a 1 on the 1 sensor on the bottom.
Absolutely. So the red cylinder is being pulled inward, but the white cylinder is still on the ground. So we still have 1, 0, which means we're still sending 0.7 to the joint, which means the joint is still being commanded to rotate inward to an angle of about 40 degrees. So this red cylinder will start to accelerate inward and downward towards the white cylinder, and that process will continue for 20 or 30 time steps until the red cylinder hits the ground. What happens at that point? What's changed? Let's go from the sensors to the motors.
Well, so that both sensors are going to be firing.
Both sensors are firing, yeah.
Which means the motor's getting a signal of 1, which means it's going to tell the joint to come to 45.
It's going to come to 45, right? So now there is an even more excitatory influence on motor neuron 2. So both of these are firing. So this is at its maximum positive value, which means now the red cylinder is being pulled in with even more strength, right? It's being commanded to reach 45 degrees. We'll do one more time step. What do you think happens at the next time step? The moment there's that sudden acceleration inward of the red joint, the red cylinder, the moment it touches the ground.
It springs off the ground.
It springs off the ground, right? And at this point, our intuition breaks down, right? It's not clear whether both of them come off the ground, the red one comes off the ground, the white one comes off the ground. One or both are going to come off the ground, which means the sensor values are going to change, which means the signal that's being sent to the joint is going to change, and now it's going to suddenly change how it's moving again.
I just had 2 questions.
Sure.
One more about like specifically how the simulation works. I've
Okay.
noticed when you run it and it's just like the normal joint, it'll fall down on itself and then it'll fall to the right. What force is pushing it to the right?
No force is pushing it to the right. So you'll notice after a while the robot will fall to the left or the right.
Mm-hmm.
The reason why is that the physics engine is simulating Newtonian mechanics for you, which is just a fancy word usually for this. We'll get to this in lecture 6 today. So the physics engine is calculating all the forces that are acting on the objects. None of them are pushing to the left and the right. Okay? And if we divide by m here, we get acceleration equals equals force divided by mass. So the physics engine knows the masses of these two cylinders. It knows all the forces that are acting on the cylinder, so it can compute the acceleration and thus the new positions and orientations of the objects. The physics engine, however, is doing this using floating point values in your computer, which have a finite accuracy, right? So as you run this for enough time steps, there's a little bit of error that starts to creep in because it's approximating, it's not perfectly computing acceleration based on forces and masses, right? It's pretty accurate, but eventually those approximations catch up with the system, and this is not a perfect approximation of Newtonian mechanics, and falls over. That's why, right? So again, coming back to the reality gap, in reality, you will move exactly as the forces acting on your body dictate. In a physics engine, not quite, right? Maybe to 20 decimal places, but not 21 and not 22. Doesn't matter for the first few time steps, but those approximations start to accumulate after 50 or 100 time steps, and you get these funny things happening.
And then also the
Yep.
sensors are on the, I want to call it the vertex of the semicircle, and so if it falls to the side, it'll loosen up again.
You mean the touch sensors?
Yeah, the touch sensors.
So the touch sensors, I'm approximating those in PyroSim. So if any part of the cylinder surface comes into contact with anything else, the touch sensor fires.
Okay.
If you want to be more specific than that, you need to add additional smaller objects on the outside of your cylinder and put the touch sensor in there. Right? So our robot doesn't have skin. It can't detect local collisions. All it knows is that the entire object has collided somehow. Right? Okay. Any other questions? Okay, so by the end of assignment 4 next week, you will have a robot in the full sense of the word because you will have closed this feedback loop between the robot and its environment. Right? The robot pushes against the world, and it observes how the world pushes back. Right? You'll notice that in assignment 4, in the synapses project here, we've wired in some of the sensors. So some of the sensors are influencing the robot's behavior. In this case, the 2 touch sensors. The other 2 touch sensors, the proprioceptive sensor and the ray sensor, they're still recording information from the external world, but it's not influencing the robot's behavior. Right? So this is something to keep in mind when you start building your own robot. You can put sensors in the robot and even sensors in the environment just to record information from what's going on in the simulation. You don't need to necessarily have all of those sensors influence behavior. It's up to you. So far, so good? Any questions about assignment 4? No? Okay. Okay, so let's return to lecture. We were working our way through evolutionary algorithms last time in lecture 5. We were talking about evolutionary algorithms and how they are an approximation of biological evolution. When we use an evolutionary algorithm to optimize robots, we have evolutionary robotics. And we ended last time by looking at this this metaphor called the fitness landscape, which is sort of a tool we're going to use to try and mentally visualize what all of these different evolutionary algorithms are doing. In essence, an evolutionary algorithm is a search algorithm, which is searching over, in most cases, an infinite set of candidate solutions to your problem. In our case, a candidate solution is going to be a robot. And by doing so, it's kind of sprinkling points through this space. Each point corresponds to a particular candidate solution. The horizontal position of that point is dictated by the solution's genotype, right? And the genotype might have one dimension, like we see up here. We might have one gene. The genotype might have 2 dimensions. We might have 2 genes, in which case we have a 3-dimensional fitness landscape. The reason why this is just a metaphor is because once we get into large numbers of genes, we have a very high-dimensional fitness landscape, and we can't draw it, and it's hard to visualize, right? But even in high dimensions, we have a number of horizontal axes, each one or horizontal dimensions, each one corresponding to one gene in the genotype, and the vertical axis is always the fitness of that candidate solution. The higher that point is in the space, the better the candidate solution is. We're measuring the fitness of the phenotype, right? So we're going to distinguish between genotype and phenotype. The genotype is the genetic blueprint, right? It's all the instructions for how to build the phenotype. So in our case, the phenotype is the robot, what the robot looks like, and how the robot behaves. Okay, so we ended last time by talking about the hillclimber, simplest possible search algorithm you can imagine. Drop a single point, produce a child that's nearby that point. If the child is higher in the space than the parent, keep the child. Otherwise, delete the child and produce a new child from the parent. We saw that there's a problem with the hillclimber, which is you might get unlucky with your initial parent. It may fall on the slope of a local optimum, and even if it starts to climb its local slope, it's going to get stuck on a local hill, right? In the case of robotics, you might get a robot that moves relatively quickly, but it's got a limp in its gait, and it's very difficult for evolution to ever remove that limp and get the robot to move very quickly because it can never get off this local peak. Yes?
Is that a graph or a hill?
Is what a graph or a hill?
The top right.
My cartoon here?
Yeah.
So this is, so it's a graph, right? So we have a number of axes here, and there's a point at each point in this, along this horizontal dimension.
So do the arrow direction, how come one's going backwards and one's going forwards along the...
The arrow of the axes here?
Yeah.
So this just indicates that there's a range here. Maybe this is not the full range of...
Well, not the arrow on the axis, but the arrow from P2 to C2 and P1 to C1.
This is showing the difference between the fitness levels between the parents and their children. So in one case, they made a random child on P2 that had a higher fitness level than the P2. And so they would throw out that parent. But in P1's case, its child was not as fit as itself, so it's going to throw away the child.
Okay.
It's just a random draw.
That's it. So the arrows here, this is my little cartoon showing that this parent produced this child, right? And it's horizontal, the child is horizontally distant from the parent because its genotype is different. We've mutated the genotype. And the height differential, as you mentioned, is the difference in fitness between P and C, right? So in our parallel hill climber here, we have 2 parents, P1 and P2, and each of the parents has produced a child. C1 is less fit than P1, and C2 is more fit than P2. So at the next generation, C2 is going to replace P2 and become the new P2. The child outcompeted its parent. In the case of P1, C1 is deleted, and P1 produces a new C1. Right? It's a parallel hill climber. We've dropped multiple points into this space, and each point is producing children that are nearby, and around we go. Make sense? Okay. We mentioned, again, even a parallel hill climber has a bit of a disadvantage, which I've tried to show by this cartoon here. In most fitness landscapes, there are large numbers of local optima. There are millions or billions or trillions of these local hills. So even if we sprinkle a lot of initial P's within this space, it could be that all of them still get stuck on local optima. Right? And the reason why is because each individual point is still a hill climber. It's still only producing a child that is near to the parent. Right? A parent very rarely produces a child that's very different and happens to land over here somewhere else and might start to climb a different hill, which might actually turn out to be the mountain, the global optimum. Right? This is a problem that Mother Nature faced for billions of years until she invented sex. Right? So in the genetic algorithm, again, we're marching forward now. This is our third search algorithm. This is getting a little more complicated now. Like the parallel hill climber, we start by sprinkling a number of points randomly in the space. We create a number of random genomes. And we allow mutation like we did before, but every once in a while we take two parents, we cut the parents in half, each of the parents in half. We take the gene values from parent 1, copy them into child 1, and we keep copying from left to right until we hit the crossover point. Then we switch from the crossover point to the parent 2, and now we copy the gene values from parent 2 into child 1. So child 1 now, the first half of its values came from parent 1, and the second half of its values came from parent 2. Right? We're combining genetic material from two parents. We also can produce a second child, and the second child is the inverse of the first child. We copy the first few values from parent 2 into child 2. When we hit the crossover point, we jump to the other parent, which in this case is parent 1, and continue copying the genetic values from parent 1 into child 2. Right? Genetic recombination. So why is sex so valuable from an evolutionary point of view? Because every once in a while, when you recombine genetic material from two parents, you bring together the best of both worlds, right? It might be that in parent 1, whatever this candidate solution is, it turns out that these values are actually close to what they should be. And remember, we don't know what they should be. If we did, we wouldn't have to run an evolutionary algorithm at all. But this part is somehow increasing the fitness of this parent, but these values are wrong. In parent 2, perhaps these values are pretty close to the correct value. These values helped increase the fitness of parent 2, but these values are wrong. If we take these values and combine them with these values, now we get a child that has brought together two good subproblems and does better than either parent. You'll remember last week we were talking about a neural network that solves the XOR function. And in that network, there were two subnetworks, one that computes the OR function and one that computes the AND function. Imagine we had two neural networks, one which was successfully computing the OR function, but was doing something wrong in its second part. The second neural network was computing the AND function, but the other part was doing something wrong. If we crossed those two networks in just the right way, we might bring together the OR function and the AND function into the child, and the child might solve the XOR function, assuming it also had the synaptic weights out from those two subfunctions correct as well. Right? Okay, so again, we can say that verbally, bring together the best of both worlds, but what does this really look like? Again, we can use our fitness landscape to understand what's actually going on. So let's imagine, again, following this cartoon example here, we have P1 here and P2 here, and they are far from one another on the horizontal axis. What does that mean? If 2 points in the fitness landscape are very distant from one another horizontally, what can you tell me about P1 and P2? Forget about their heights for a moment, just their horizontal distance.
A lot of genetic diversity.
A lot of genetic diversity, right? They're very different genetically from one another, right? If we combine their material together, we're actually making a pretty big change in the genotype, right? If you look at the genotype of C1 compared to P1 and P2, it's quite different, right? So C1 is also pretty far from either parent, right? It's a much bigger genetic change than just taking a genome, copying it, and introducing a small mutation. When we mutate things, they tend to be close to their parent, right? When we cross genetic material, we're making a bigger move horizontally in the fitness landscape. Okay, so in this case, C2 is not very lucky. It's far from P1 or P2, but it's landed again on a hill. But it didn't escape the hill of P1, but it did escape the hill of P2. In the case of C1, it's also distant from P1 and P2. And in this case, we got lucky. Because it was distant from either, it escaped the hill of P2 and it escaped the hill of P1. And in this cartoon example here, it happened to land on another hill, which turns out to be the mountain, the global optimum. Right? So if C1 now starts to produce some offspring, so now it's taking small jumps through mutation, the descendants of C1 will probably find the global optimum. So that's a way of thinking about this idea of randomly combining genetic material from two individuals, and that can, in some cases, bring innovation. Suddenly you have a child which is quite different from either parent and happens to combine good material from either parent and through subsequent improvement does something better than either parent. Any questions about this? So this is known as the genetic algorithm. So the genetic algorithm differs from the parallel hillclimber in the sense that the parallel hillclimber only implements mutation. The genetic algorithm includes both mutation and recombination. The genetic algorithm is the most common of all evolutionary algorithms out there. Sometimes the genetic algorithm is used as a synonym for evolutionary algorithm, but in reality, evolutionary algorithms is an umbrella for a large class of evolutionary algorithms. Yes?
So say C2 is not as high as P1, but C1 stays higher than both. Does the lowest value get replaced?
Okay, that's a good point. So I didn't talk about who lives and who dies in this situation. So I forgot to mention that. So in a genetic algorithm, remember we have a population initially of parents. So we've got a whole bunch of parents in the population. All of those parents produce, either one parent produces a child. Sometimes that occurs. Sometimes two parents are recombined and produce two children. So we just grow our population. We just keep adding the children to the population until we've doubled the size of the population. Now we have n parents and n children. We compute the fitness of all those new children. Now we know the fitness of all the parents and all the children. We know the heights of all the points in this fitness landscape. We now sort the population from highest fitness down to lowest fitness. So now we have a sorted population with higher fit individuals towards the top and low fit individuals towards the bottom. And that usually mixes up the parents and the children. What do you think we do at the next step? I've just walked you through creating the random parents, evaluating them, and now we want to select and vary. What's going to happen now? We need to select. We've got 2n individuals in the population. We need to get back to n. What do you think we do?
Take the best. like top half.
Take the best top half, right? So everyone who's in the bottom half, you're gone, right? So now we're back to N. We relabel those as all the N parents. Do it all again and again and again. Sorry, I forgot to mention that. That's the full genetic algorithm, which you'll be doing in assignment 7. Okay, let's move on. There are still problems with this algorithm, so let me show you the problem first, and then we'll talk about the solution. So let's go back to, forget about recombination for a moment. Let's just think about mutation. So let's imagine that we have this fitness landscape here. We have a single parent here. And the parent is going to produce children. And those children are going to be slightly distant from it along the horizontal axis. You'll notice it says here step size equals 0.1. So 0.1 is going to be the distance in genotype space here. So remember, in this two-dimensional fitness landscape here, we have the genotype is made up of just one gene, and that gene can take on different values. Whatever the value of gene 1 is in this parent, let's assume that we're going to mutate that value to be either 0.1 greater than this value or less than, or 0.1 less than this value. We're going to pick a new value in this range, and that's going to be the child. Given that range, half of the children can be worse than the parent, and half the children can be better than the parent. So even if this parent produces a child, and it's to the right of this parent, the child is worse than the parent, the child dies off, we do it again. There's a 50% chance that eventually we're going to produce a child that is better than the parent, right? We're all good. We're going to keep climbing this mountain and eventually get to the top. Let's imagine now that we have this fitness landscape. This is a much more rugged fitness landscape, and we're going to talk about rugged fitness landscapes throughout this course. You can see visually what I mean by a rugged fitness landscape. There's lots more of these hills in this space. Imagine we now have this parent, and we're still applying the same mutation operator. Whatever the value is of this gene, when we produce a child, we're going to increase the value up to 0.1 greater than this value or less than 0.1 of this value. What's the probability that that parent is going to produce a child that's better than it? In the previous case, it was 50-50. What's the chance now? Drastically less, 20, 10, I don't know, right? The only place that the child can land is slightly less than the parent, right? This might take quite a while to do. Even if you do get lucky and eventually produce a child here that is more fit than the parent dies off, and now we keep the child, and that child is going to produce mutants that are anywhere in this range. What's the chance that this child is going to produce a grandchild that's better than it?
Even smaller.
What's that?
Even smaller.
Even smaller, right? So we might start climbing this hill, but it's going to take longer and longer and longer and longer to do so, right? This is somehow unsatisfying. So here's a little cartoon of this situation, right? Things don't look very good on a rugged landscape. It's going to be very hard to do this. What we'd like to do is be able to kind of shrink this range when things get difficult, right? We want the mutants of this one to be more similar to the parents, right? So if you take something at random and you start making changes to it, you've got a pretty good chance of making it better. But as it starts to get better, there are fewer and fewer things you can do to improve it, right? You get diminishing returns here. But evolution doesn't know that, right? It's making these big changes, +1, -1, or +0.1, -0.1. Can we get evolution to figure out how to do this on its own? Can we get evolution to tune the magnitude of the mutations?
Well, yeah, couldn't you just say, like, you know, after X number of runs, if we haven't found anything, to make it less and less terms of the amount of change.
We could do that. So we could give evolution an additional heuristic and say, if you go 20 or 30, if you produce 20 or 30 children and things don't get better, shrink your mutation. You could do that. It turns out that there's another evolutionary algorithm called the evolution strategy, which is an even more elegant solution, which is let evolution figure out how to shrink or even increase the mutation rate. It might be that it's climbing a narrow hill and jumps off that hill and manages to land on some other slope, and that slope is broader. In that case, it should sort of open the throttle again and start moving faster, right? It's making improvements. So in the evolution strategy, like all the other ones we've seen before, we have a genotype, which is made up of a bunch of genes, and each gene has its own value. And each gene also has associated with it a step size, or what's known as a strategy parameter. This value here says if this gene gets selected for mutation, change this value within a range of plus or minus 0.1. If this gene gets selected for mutation, change it by up to 0.2 or down to minus 0.2, right? So this gene might suffer a larger mutation than this one. This one has a much smaller step size. Right? So in our little cartoon over here, we're just looking at one gene so that we can look at a two-dimensional fitness landscape. Remember that our fitness landscape is usually in high dimensions, which means the hill or mountain that a point is sitting on is high dimensional. It's not just moving left and right, like in the cartoon here. It might also be moving forward or backwards or along other horizontal mutations. So along one dimension, the hill might be relatively broad, meaning you're free to make relatively big jumps along that horizontal axis. But along another axis, the hill might be relatively narrow, like these, and the gene should make a relatively small jump. It's hard for us to kind of figure that out and tell evolution a priori, so we just tell evolution, you figure it out.
Does the thing know the slope of the point of the graph that it's at?
Absolutely, it does not know the slope, right? This is always the tricky part. All the evolution algorithm knows is where it's standing, right? It knows its height. It doesn't know the slope or what's in other directions unless it produces a child over there and the child is higher or lower. Where do these numbers come from? We can't set them a priori. We don't know the slope of the mountain. The point doesn't know the slope of the hill that it's sitting on, so it can't set those values based on the slope of where it is. Where do these numbers come from? Where did these numbers come from? We didn't set them by hand, right? You didn't type in 0.3, 0.4.
Sensor?
Not from the sensors. We started with a random set of numbers, right? And then evolution started going. So these numbers are being set through mutation and recombination, right? Evolution is changing them, and the changes that increase the height of the point stick around, and the changes to those numbers that don't die off, right? These gene values are evolved. So where do you think these values come from?
They're evolved.
They're also evolved, right? So we, in essence, now have a matrix genotype rather than a vector. It's a 2 by n matrix, right? Every gene value has its own step size. And depending on the step sizes associated with the genes in the genotype, that genotype may survive or not, right? If you have an individual sitting down here, and the step sizes are all large, they're far from zero. Imagine you have another point which is sitting at exactly the same place, which means it has exactly the same gene values, but all of that second individual's step sizes are very small, very close to zero. Which of those two has a better chance of survival, and why? They have exactly the same genotype, which means they sit at the same place in space. They have the exact same height, they have the same phenotype, but different step sizes. Which one has a better chance of survival? The one with large step sizes or the one with small step sizes? Yes. Small, right? So this guy, which we already talked about, he's producing children that are far from him in the space. All of his children are dying off. The one that's sitting here and is producing children that are much closer to it, those children are likely to survive and continue on the genetic material of this parent. Right? So indirectly, evolution can figure out what these step sizes should be. So now we have an evolutionary algorithm that is not just moving points through the space, but it is also figuring out the velocity that those points should move through space. How fast or how far should they jump away from the parent? At the beginning, the velocity might be high, right? They're climbing the shallow initial slopes of hills and mountains, and as the descendants get higher and higher reaches of the mountains or hills, evolution will start to reduce the step size and make smaller and smaller jumps to get to the top. Make sense? Okay. Let's carry on. Up till now, we've been looking at evolutionary algorithms that encode the genotype in either a single number, like we started with here, or a vector of numbers. And we ended with an evolutionary strategy which the genotype looks like a matrix. Let's now look at a different evolutionary algorithm called, genetic programming. So in genetic programming is usually applied to a particular problem called symbolic regression. I apologize, these slides should actually be labeled genetic programming, which is the name of the evolutionary algorithm. And we're going to build up an intuition for genetic programming by applying it to a particular problem, which is called symbolic regression. Okay, so here we go. Here's genetic programming. As you can already see, the difference between genetic programming and all the other evolutionary algorithms is now the genotype is encoded as a tree. So we have two individuals in the population here, P1 and P2. We can see that each one has a tree. Here's the root of the tree. Here are the leaves of the tree. And we can already see that these two individuals have different numbers of genes. So not only are we encoding the genotype in a different data structure, but now we've got genotypes which are larger or smaller than each other. In all the other algorithms we've seen, we've had a fixed length genome, right? We're pre-specifying the number of genes. Okay, so what can you do with genetic programming? Why would you want to encode the genetic material as a tree? One thing you might want to do is try and solve this problem known as symbolic regression. Here's the symbolic regression problem. Let's imagine that we want to try and discover an equation. We've got a whole bunch of data. We want to try and generate an equation that describes that data, but we don't know what that equation is. So now, instead of evolving synaptic weights in a vector, we're going to evolve populations of equations. And the fitness of any individual equation is how well it explains the data that we have. That's the general intuition for the moment. Okay, so we've got two individuals here. Each of them is encoding two equations. What equation does P1 encode? So for the computer scientists here, you're going to have to remember your infix and postfix notation here, prefix notation.
0.8 plus x times 1.4.
That's right. So 0.8 plus x times 1.4, and the next one is?
0.2 over x plus y.
That's right. 0.2 divided by x plus y. So if you haven't come across this in your computer science classes, that's fine. There's a trick where you can take arbitrary equations and encode them as trees, where the internal nodes in the trees are operators, and the leaves are operands, which could be variables or constant values. Okay, so where did these two equations come from? Well, we're going to generate them, like always, by starting with a random population. So we're going to create, let's say, 100 parents. We're going to create a population with 100 individuals in it. Start with P1. And when we start to create P1, I'll come back to this slide, but let me back up for a minute. By reaching into a bag, and in that bag is a whole bunch of possible operators and possible terminal nodes or operands. So I'm going to create P1 at random. I reach into the bag, and I happen to pull out molt. So I put molt at this node. Molt takes 2 arguments, which means I need to create 2 subtrees. So I create a left subtree that's initially empty. I reach into the bag again. In this case, I pull out plus. Plus also requires 2 arguments, so I create 2 empty subtrees. I come down here, I reach in the bag again, and I happen to pull out a random constant, 0.8. It doesn't take any arguments, so I'm done. I come back up here, I have an empty node here, reach into the bag again. In this case, I happen to grab a variable x, almost done. I see that I have one last empty node over here. I reach into the bag again. In this case, I happen to pull out 1.4. Done. I've created a random genotype for P1. I haven't evaluated P1 yet. I don't know what its fitness is, but I've created its genome. I take P2 and start reaching into the bag again and keep doing that until I have a tree for P2 and do that for all the other 98 parents in the population. I now have 100 random equations, and I want to know how good those equations do at fitting the data, or explaining the data that I have. So far, so good? Okay. So again, I'll talk about the data in a moment, but let's have a look at mutation and recombination. We saw what that looked like in the genetic algorithm. What does mutation and recombination look like in genetic programming? Let's imagine that we've done a little bit of evolution and these 2 parents have survived. Some of the other parents have died off. So we grab this parent here, and we're going to do recombination first. We'll do mutation in a moment. So let's take P1 and P2. Remember that recombination in the genetic algorithm is we march along and copy one part of the genotype of parent 1, switch to parent 2, and copy the rest of the genes in parent 2. We're going to do exactly the same thing here. We're going to pick the crossover point, and let's say we pick this point as the crossover point. You'll notice it's the same in both parents. How does recombination go from there? We've taken our 2 parents that are going to have sex. We've picked the point where we're going to cross them. What happens next? How do we produce C1 and C2, the children?
Over.
Off you go, right? Simple as could be. We're going to pull off these 2 subtrees and swap them. And we've got 2 new trees which have different form, right? We're crossing the genetic material from these 2 parents. And now the genetic material that was originally sitting here at P1 has ended up over here in C2, and the genetic material from P2 has ended up in C1. And if you look at the equations for C1 and C2, they look similar to, but not identical to, the 2 parents. Okay? We've recombined genetic material in genetic programming. That's crossover. How do you think mutation works? So in mutation, we have one parent, and we're going to produce a child that is very similar to, but slightly different from the parent.
You just take a node and then reevaluate an element within it. And
So we grab a node, right? We have to figure out where the mutation is going to occur. Let's say you pick this node in P1 for the site of mutation. What do we do at that point? We need to mutate the tree at that point. How are you going to change the tree at that point? What did we do in the genetic algorithm? We had a vector of numbers. We picked one number. What do we do to that number?
Alter it.
We alter it how?
Subtracting, adding.
We just do something random, right? It's a mistake. So how do we do something random here?
just grab from the bag. and
Grab
pull
from
out
the
the-
bag again, exactly. So we take 1.4, we erase it from that node, reach back into our bag, and maybe in this case, we pull out div. So we put div in here. We have to create two subtrees because div takes two arguments. We pick 1 and 2. 1 divided by 2. We've got a new child, C1, which is similar to, but also slightly different from the parent. So far, so good? Okay, so we now know how to run our evolutionary algorithm. The last thing we haven't explained is how do we compute the fitness of any one of these trees. Okay, so let's look at some data now. Let's imagine we have a relatively simple data set. We have our independent variable here, x, something that we can set. And whenever we set x, the environment gives us back a value of y. So we do some measurement on x and we get y. We do that for a bunch of x's and we get back a bunch of y's. And we'd like to try and understand the relationship between x and y.
A quick question on the last slide.
Sure.
When you're mutating these,
Yes.
you have to set a limit on the height of the tree.
Good catch, right?
Because
Because what could happen?
Go forever.
You could end up going forever. So usually when genetic programming is implemented, you just put some maximum depth. What happens when you're creating a tree and you get to that maximum depth? How do you stop?
You have to put a terminal node.
That's right. So now you reach into only one part of the bag that contains the terminal nodes. Yep, good catch. Okay, so here we've got a data set. Recall your high school algebra. You're going to run symbolic regression in your head. What is a good equation that explains this data set? Y is equal to something. X squared. Sounds pretty good. Now really recall your high school algebra. Okay, sounding better, right? So you're running symbolic regression. X squared is a good start. It's not quite correct. There's a slightly better equation, right? Okay, so how do we usually do this? So we can run this in our head, but if I gave you a more complicated data set, it would be very hard to figure out just by looking at the data what the equation is. $1 million question out there in machine learning at the moment is exactly how to do this, right? How do you come up with a compact equation to describe all of the big data and complex data that our world is generating? Not an easy thing to do. What's the standard way of doing this? Standard way of doing this is linear regression. So linear meaning a line. Take a straight line and drop it into the plane so that all of the points are as close to this line as possible. What do I mean by as close as possible? We want to compute the error of this particular model. So y is equal to x. Sorry, there's a little typo on the slide here. So y is equal to x is this line here, and these little thin vertical lines is the amount of error, right? How far the point is from the line. If the points had happened to look like this, then dropping a line right at that point would be great, right? So there's methods out there to kind of move this straight line around to minimize error. How good are we going to do? Not great, right? There is no line. There is no straight line that will approach very close to all these points. So unfortunately, linear regression doesn't work very well for even this simple case, and in most real-world data sets, forget about linear regression. Y equals x, or any linear equation you could write down here, ain't going to cut it. So we need to do nonlinear regression, or what's known as symbolic regression. So now you can probably figure out what this term means. Symbolic regression means we're not going to assume the symbols on the right-hand side. We're not going to assume that it's y equals alpha, mx plus b, right? And try and figure out what m, or the slope, and b, the y-intercept, should be. We're not going to assume it fits that form, mx plus b. We're going to assume that it might actually, the symbols might be more complicated on the right-hand side. Okay, so let's imagine that we ran genetic programming and one of the trees in that population was a tree that had a single node, and in that node was x. That tree would be encoding y equals x. We would compute the error of that tree, and the error would be pretty high, right? This particular equation generates large error. So what do you think the fitness of this tree will be? Low, right? So we can set the fitness to be 1 over e, right? Or 1 over 1 plus e if you want. Doesn't matter. It's the inverse of error. The more error, the lower your fitness. perhaps there's another tree in the population, or we evolve a tree of this form, which is much closer, right? This one has much less error and therefore higher fitness, and it's probably going to outcompete and kill off this equation. Are we done? Are we at the top of the mountain? What's the equation that sits at the top of this mountain?
Maybe add 1 to that.
X minus 3 squared plus 1. Maybe. I guess we could draw it and figure out. I think you're right, actually. That might actually drop error a little bit. So let's assume that that one does have higher error. So now we've moved to x minus 3 squared plus 1. Are we at the top of the mountain?
Probably a polynomial of power 16, since there's 16 nodes. You can probably get it to hit each one.
You can definitely get it to hit every node exactly, right? And you're going to get a frighteningly large polynomial, or x divided by x plus sine x to the power of cos e to the x. You'll get something horrendous. Okay, so now we already see there's a bit of a problem here in symbolic regression. I can give you a simple equation, which is a linear approximation. Not very good. This is definitely not very satisfying. This, better, but a little more complicated. Still doesn't explain all the error all the way up to some ridiculously complex equation. Which one is the right one? Well, we know which one is the right one. Which one is the most satisfying one?
This on the right.
Perhaps, right? Remember when we were, there is no satisfying one. There's something in the middle, right, that probably works for us. Remember when we were talking about artificial neural networks last week? What was one of the big problems with artificial neural networks? Or one of the big challenges? Overfitting, right? We got this big neural network which reduced the error in our training set down to 0, but did it by memorizing all the data. Same thing's happening here, right? Just in a different form. This is one of the biggest challenges at the moment in machine learning research, which is overfitting. You want to try and find that sweet spot between a high error over approximation and a low error overfit solution.
So just arguably it's what does the person who is looking at it want? Because if I see a polynomial like that and I say, well, I could see a cosine with this would have looked way better, and then I would say that that's a better graph for it. But then someone else would say, I don't want to look at trigonometry right now.
Perhaps, right? So maybe you give them a palette, right? You sit with y equals x on one side and your order 16 polynomial on the other side, and everything in between, and let them choose.
And that's what the r squared value is on calculators whenever you...
Yes, that's what r squared is. Okay, we're going to see this come up again later in the course, a way to deal with the situation that there's actually two things here we're trying to optimize. We're trying to minimize error, and we're also trying to minimize complexity. There's two things we want to try and improve here, and we'll talk in a couple weeks about an evolutionary algorithm that's able to try and deal with two or more components of fitness. Okay, got a couple minutes left, so let's look at some actual data. Some of you may know that Lake Champlain, just down the road, suffers from time to time algal blooms. Some summers there's no algae, other summers there's lots of algae. Some summers it's in Mallett's Bay, some summers it's in Missisquoi Bay. No one is able to predict when and where or if an algal bloom will occur in Lake Champlain. There's a multi-million-dollar research project going on right now at UVM to try and solve this problem. Some of the researchers who are working on this are using symbolic regression. So if you've ever taken Professor Epstein's evolutionary computation class, she might have mentioned this. She's working on this problem. All right, so let's look at this data set. Here's the thing we want to predict, right? So this is y in our case. It's the amount of algae per milliliter in the lake at a particular place. And here's our data set. So every row corresponds to an observation in space or time. This observation was made in August of '99 in Mallett's Bay. This one in 2000 in the same place. And we're going to measure a bunch of variables, independent variables, which are thought to be predictive of the outcome. how much nitrogen is in the water, how much phosphorus is in the water, the temperature of the water, what's the turbidity, how opaque is the water, is it clear or turbid, how much rainfall occurred in the last 24 hours, and so on. That's the data set. Pass that through symbolic regression, and one of the first things that it will give you back is P equals T. What does that mean?
It's linear.
It's linear. It's the first thing it gives you back. So P equals T, what does that mean in this data set?
It means that the amount of phosphorus is very closely linked linearly to the amount of algae.
Exactly, right? So let's go back to our y equals x. So the more phosphorus there is at that point in the lake, the more likely the researchers were to have measured actual algae concentrations at that point. However, it's pretty good, but still relatively high error. So the next thing it tends to find is n divided by p equals t, or p divided by n. I can't remember. It's one of those two. What does that mean? Slightly more complicated.
The ratio of the nitrogen and phosphorus.
It's not just, if you want to try and predict algae, you can't just measure the amount of phosphorus. It's not just that more phosphorus means more algae. It's part of the problem, but it's also the ratio between n over p. And I haven't seen the latest equation, but it's n to the cube divided by the cos of p times w, and so on and so forth, right? It starts to get more complicated from there. But this is important for environmental scientists because they want to understand not just what are the culprits of algae, but what are the interactions between those culprits, right? It's the relationship between N and P, right? And once you understand those relationships, there might be certain things that we can do to tamp down algae in the lake, right? Farmers are going to keep putting fertilizer on their fields. That might not be something we can control so much, but maybe we can control the relationships of things. If there's more P, maybe we actually dump stuff in the lake to make that relationship closer to damping down algae. Again, it may be not something we want to consider doing, but there are other things we might be able to change about this system to reduce algae because we have a more accurate picture of what's going on, right? It's not just about the amount of P, it's something else going on. Okay, we got 2 minutes left, so let's finish up here. This is a fun one. You can go Google this and have a look. I think if you Google genetic programming and Mona Lisa, you'll find it. What I'm showing you here is actually I'm showing you the phenotype. So the phenotype is now not an equation, it's a picture. So now we're going to use a tree to encode a picture, and the fitness of that picture is how close the pixel array generated by that picture is to the actual pixel array of the Mona Lisa. We're trying to evolve a picture that more closely approximates the Mona Lisa. Here was one of the first random trees, and over the generations of genetic programming, you can see it gets closer and closer to the Mona Lisa. You can see by looking at these different pictures, there's clues in here about how these pictures are encoded in genetic programming. Remember that there's a tree behind each one of these pictures. What do you think the internal nodes and the terminal nodes are in those trees? What's not just what is a good genotype, but what is the genotype? What can you see in these intermediate pictures? Tell me about these pictures.
Somehow working with opacity and RGB values.
Yes. Opacity and RGB values. Opacity of what?
Well, the different polygons.
Polygons, right? So you'll notice that these images are made up of multiple polygons. So each subtree in a GP tree in this application, each subtree specifies a polygon. And when you get down into the terminal nodes, each of the terminal nodes indicates a vertex of that polygon. So if you have a subtree and it ends up having 9 terminal nodes. Those nodes specify the 9 vertices of that polygon, and it also encodes a number, which is the opacity. So you can see that some of these polygons are lying on top of one another, and they're transparent. So if I mutate my tree, and I add a subtree, I add a polygon. If I mutate my tree and I delete a subtree, I delete a polygon. I can also mutate the vertices, and so on. We then take that stacked set of polygons and push through at each vertex and compute the RGB value of that pixel, and that gives us a pixel array. How do we compute the fitness now? We're almost there. We've got the genotype, which is the tree, the phenotype, which is this polygons that get translated into a pixel array. We've got one more step to go, which is the fitness. What's fitness here?
Can you just check the pixel array RGB values and compare it to the original and see how accurate it is?
Absolutely, right? So not that different from what we did here, right? Take the actual pixels from your phenotype and look at the error or the distance of the color of that pixel to the color of the pixel from an actual picture of the Mona Lisa. And if you run this, this is what you get. Okay, so I think we will stop there. Frank, can you put up your hand for a minute? So Frank will be your guest lecturer on Tuesday. Assignment 3 is due Monday night. You have a quiz due tonight, and I will see you next Thursday. Have a good week. Thank you.